Hi class, welcome to the next section, chapter 5. In chapter 5 we're going to kind of just talk about some of the uses that we have for derivatives. We're not going to go over all the uses. Some of those are going to be reserved for chapter 6 as well. But these are some of the main uses of using derivatives and their applications to some of the sciences and some of the different areas of mathematics. So what we're going to talk about today is linear approximations and differentials. Okay, so we know that the derivative has three different notations, but we really only use two. We use the prime notation and we use the Leibniz notation. The Leibniz notation is something divided by something else, but we never really talk about it as dy divided by dx. We see it as d over dx, and we know that we are differentiating with respect to x, or we'll see df dx, and we know, oh, our function f, we are differentiating with respect to x, or dy dx is the same thing. But we haven't talked about what those things are separately. Like, what is dy? What is dx? Right? We haven't talked about that. We've just talked about dy over dx as a whole, and we called it the derivative. So here we're going to talk about that. Those are actually called differentials. And we're going to talk about how we use linear approximations, or what is called linearizing a curve. So let's say that we have a function, f of x, and we know its derivative because now we have all the rules and techniques available to us for finding derivatives. So we know what f of x is, obviously, and at this point we can now find a derivative. We know that the derivative is the slope of the tangent line at any point for our function. It tells us the instantaneous rate of change, yada yada yada. We've talked about this several times in pretty much every section since chapter 2 or 3, right? Let's say that we have a point of interest, okay? And so this is a fixed point. So we're going to call this point x naught and y naught. So we're going to put the subscripts here just to indicate to us that this is not a point that moves around. It satisfies our function f of x. Okay. If I look at, if I plug this point into my, or I'm sorry, not the point, but if I plug x into my derivative function, I know that that will give me out the slope of the tangent line at that point for my function, right? The instantaneous rate of change. So let's say that we wanted to solve for this equation. Okay, we've done this several times, but we haven't done it yet in general. We haven't generalized this. So I know that my slope is f prime of x naught, the derivative at that value of x, and I know that I have this point of contact between my function and the derivative. So this point satisfies my function and this point satisfies my derivative. So when I plug all of this into the y equals mx plus b form to find the equation of a line, I get my y equals m, which is the slope at this point, x naught, times x plus b. So the only thing I don't know here would be this value of b. So if I solve for b, it's very simple. I just subtract everything else off that's not b, right? It's not always that easy in practice when we have fractions and things like that, but that's basically what we're doing, is isolating b. So b has the form of y naught, this y value, minus my slope at that point times my input value. So if I plug this all together, the tangent line to my function at this point is given by y equals f prime, plugging in this point, times x. So here x and y are not fixed variables, x naught and y naught are, right? So this is mx, and then this whole thing is my b. So y naught minus f prime of x naught times x naught. So this is the generalized form for a tangent line for your function at any point, okay? Your choice of points of x naught and y naught. So we can start to move things around to make this a little bit easier to look at, because I mean there's a couple of things in common here, right? For instance, I have two f naught of x naughts. There's x naughts everywhere, right? So let's start to try to simplify this. So we will factor out this f prime, okay, for the two terms that have it. So I have my f of x naught plus f prime of x naught, x minus x naught. So you might also recognize this from the point slope form. So this is just us kind of reorganizing things. So this is a generic form. When our input values are very close to this fixed point that we have, right, in the neighborhood of x, then we can say that our tangent line is a very, very good approximation for our function, right? Because the difference in values are going to be very, very small, right? Only when I'm close to the point of contact. When I get far away from the point of contact, obviously my line kind of goes very far off away from my function, from my curve. But when I'm close to this point, the inputs and outputs are very, very similar to my function. Okay, there's going to be some error there, but it's very, very close, right? And so this is useful because this creates what's called a linear approximation for my function, right? The tangent line is a linear approximation for my function when I'm close to that point of contact. So what this does is it allows me to, again, what's called linearize my function. So let's say I have some crazy function with e to the x everywhere, a natural log, and x to the 50th, and I want to analyze my function or just kind of see what's happening around some area, but it's really hard for me to plug in points. It could be possible that the derivative of this function is very easy to calculate, and so that this line now is a lot easier to look at than a very complicated function. So then instead of looking at this complicated function and trying to figure out what values I have when I'm around here, around my point of interest, I can just use this line instead. Okay, so that's what is going on here. It allows me to linearize my function near a point. Okay, this is useful because, one, it makes it easier for me to calculate stuff, but it also decreases computation times for algorithms, right? So if you're running a computer program or a video game or something like that, or creating an app, sometimes a linearization will give you a value that's good enough for your function rather than using a specific, function that's hard to calculate and has a large calculation time. Okay, so my function is basically the same, right? It's approximately the same as f of x naught plus f prime of x naught times x minus x naught. So a complicated function is pretty much the same as a line when I'm close to that point of contact, right? We call this L subscript f of x. This is the linearization of f. Okay, so my function is a function of x. So the reason I put the subscript f is to indicate that this linearization is for this function f. What if I had several linearizations, right? Each function would have a different function name, obviously, so then I can have LF, I can have LG, LH, L, whatever my function names are. Or maybe I have several f functions like f1, f2, f3, f4, so then I have linearization for function 1, linearization for function 2, so I would say LF1, LF2, LF3, etc. Okay, so now we have to do what's called an error analysis, right? I am approximating my function, so I'm not giving exact values, which means I'm going to have error, and the more I use this function, the larger my error will compound to p, or possibly the farther out I go, the larger my error is, right? So I kind of want, maybe if I want to keep my error within the tolerance, I need to be able to set a boundary. Like, I can't plug in values into this linearized function that are too far away from my point of interest. So how far can I go and still be within this tolerance of accuracy, right? So, again, the error in the approximation, it's the difference between my actual value from my function that would give me versus the output that I would get from this linearization, right? So my error is the difference in values. So my function output minus the linearization output, right? So I could replace this whole formula with just L of f of x, but then, you might be like, well, what is this again? So I just put the formula, right? So my function minus the linearization, that's the difference in values. That is the error, okay? Sometimes this value will be positive, sometimes it will be negative. Sometimes we take it as absolute value, so we just know how far away we are. If we don't take absolute value, then if it's, a positive difference, then that means my function is larger in value than my tangent line. If the difference is negative, then that means that my tangent line is an over approximation, right? It's all the outputs are larger than my actual function. So sometimes not using the absolute value is nice because it tells me if I'm an overestimate or underestimate, but the absolute value is also useful because it just tells me how far away I am, period, right? So this brings us to differentials. Okay, so let's say I have y equals f of x. This is a known fact for us. If I differentiate y, I call it dy dx. If I differentiate f, I always call it f prime, right? So these are the same thing here so far. Okay, so we can separate these, right? I bet you didn't know we could do that. So we can separate these into the two parts. So I now have everything with y on one side and everything that has to do with x on the other. Okay, so now we're splitting them into parts called differentials. So we will see this again, not only in this section. This is only a section we'll see it in right now, but when we go to the end of the Calculus 1 course, we'll see differentials one more time. Then you see them all over Calculus 2, and then Calculus 3, they're very prevalent as well. Okay, so here the differential dx is equal to delta x. And I hope you remember what delta x is. Delta x is just the change in x, right? It's the difference from one value to the next. We generally say that this is very, very small. We can say, you've seen this for slope, right? Delta y over delta x. It's x2 minus x1, or x1 minus x0, whatever it is that you use for slope. It's the same thing, right? It's your change in x, okay? The differential dy is not delta y. Okay, so that's the one thing that you really want to make sure you understand and you don't mistake. The differential dx, it is the change in x. It's you know, x1 minus x0, like I said. The differential dy is this formula that we had. Okay, it's f prime of x times the differential dx, or f prime of x times delta x. Either way, because it's equal, it's interchangeable. But the differential of y is not the change in y. Well, we'll talk about the difference in those in just a second. Okay, so well, actually right now, really. So let's say that we have a point. Okay, our point lies on our function. So I plug in x and I get out f of x, right? Let's say I have a point q, which is a little bit away from x. So if you think about limits, it's a distance of h away, right? So I'm not calling this x plus h, we're going to call it x plus delta x. So x plus whatever that change in x is. So really kind of thinking about it as like the next x value. So I'm going to plug into my function a little bit over, right? So this is my point x. I'm going to move over just a little bit, and that'll be my point q also on my function, okay? Delta y, the change in y, is the difference between my function of x plus delta x minus f of x, right? So the change in y is the change in the outputs. That is not the same as the differential, okay? So the differential of y is f prime of x delta x. Now, granted, these two values are close together in value, depending on how close my point q is to p. So again, the differential y is f prime times dx, which is the same as f prime of x times delta x. So here, if we kind of put all this on a graph, if I start with the point p, p has an input of x. It lies on my curve, on my function, right? So input of x, and its output is f of x. Okay. I move over just a little bit. Okay, so I moved over a distance of delta x. So I'm at x plus a distance of delta x. So the difference between these is the change in the x value that I chose to use. The output here is q. So on the function, that is f of this point, x plus delta x. Okay. Now, if I look at my tangent line, okay, so remember, the differential here has to do with the derivative, right? The instantaneous rate of change times a change in distance. So I have to have a tangent line here for my comparisons. So remember what we've been saying so far about the linearization of this function. So the linearization of f of x at point P is this line. So as long as I'm around P, the difference in output values is very, very small. Now if I get far away from P and I look at the outputs on my function compared to the tangent line, there's a large difference, a large error. But when I'm close to P, my tangent line is pretty much the same outputs as my function, right? Very small errors until I move too far away. And so That's what the linearization is, and that's how the differentials are related to the linearization, right? This is the difference, delta x, between my two x values, right? X and then some distance, delta x away. This is my change in y values, the output of one and the output of the other, the difference between the two outputs. My differential is the difference in height at x plus delta x. Okay, this is dy. So it's a difference from p to the same point, right? Same point of input, but not on my function, on my tangent line. So change in y is the change on my curve. Oops. Differential of y is the difference between my point and then some distance away, but looking at that on my tangent line. So that's the difference between delta y and dy, the differential of y. Okay. So again, the differential of y is the change in the output of the tangent line approximation from one point to the next. Okay, so the change in the output of the tangent line from one point to the next. So if this is one point, this is my next point. So this is my starting input on the tangent line. This is the next point of input on the tangent line. And delta y, the differential of y, is the difference in the outputs. For the tangent line, delta y, okay, delta y here is the difference in the outputs of the function, right? So delta y, change in y, change in outputs of the function. Differential of y is the change of the same outputs but of the tangent line, right? So here again, delta y is the change in output of f of x from one point to the next, and dx delta x is the change in the input that we're interested in. So here's a quick little summary of differential of y, delta y, and the differential of x, or delta x. So let's go ahead and do an example. So let's consider the following function, e to the x times cosine of x. So I mean, plugging values into here is not super fun because we have to use a calculator in order to figure out what our outputs are. Like if I said, hey, plug in 7 to this, that's not something that we can just do and mathematically find out the exact value. We'd have to actually plug it into a calculator and get some sort of decimal approximation, right? So this it's not a terrible function, but it's not the nicest, right? So let's go ahead and find the linearization of this function at x equals 0. So I have to first find the derivative, okay, which we know we have to use the product rule. So I'm going to have e to the x cosine of x plus e to the x times negative sine x. Okay, we can simplify it if we want. It doesn't really matter because we're not going to use it a lot, right? My f prime of 0. So I'm looking at the point that I'm interested in. So if we come back to our linearization function, I'm using the point of interest, right? So my point of interest, x naught, y naught, I only really need the x value for all of those things, right? So I'm going to plug 0 into my function, I'll plug 0 into my derivative, and I'll have x minus 0 for this example that we have here. Okay. So f of 0 is 1 for the derivative, so if I plug in 0, this is 1, this goes to 1 as well. This goes to 1 and this goes to 0, so I just have my 1. Okay. If I plug in 0 here, I get just 1 as well. So the linearization is 1 plus, right, this output plus the slope, x minus 0, or actually just x plus 1. Okay, very nice and easy to use. So let's say that we look at some point close to 0. Right, so not too far away. So we're at 1/2. Let's go ahead real quick and just graph these two functions. Right, we'll graph the function and its linearization at 0. Okay, so here's my function, e to the x times cosine of x. So as you can see, it's not the nicest function to look at, but luckily we're just looking at it at a nice point. Okay, and if I look at my derivative function, it looks like this. Okay, although I don't need the derivative, I just need the tangent line at x equals 0. So as you can see, it's a pretty good approximation within a certain bounds, right? So as you see, once you get to 1/2, which is what we're looking at, once you get past that, the difference in the tangent line and the function value starts to get pretty large, right? But up until this point, it's still pretty large. It's like a little more than like half of a value, right? A difference of, or I guess, 1/4, right? But here at 1/2, it's still very close in value for both of these. Okay, so we're going to look at what happens at that point. Okay, so we're going to look at x equals 1/2. That means that my change in x then is 1/2 because I go from 0 to 1/2, so the distance between that is 1/2. My delta y, remember, is the change in outputs in my function, right? So it's the change in my function values. So I know what happens when I plug in 0 to my function, so I'm going to plug in 1/2 to my function, right? Find those differences. So I'm going to get e to 1/2 cosine 1/2 minus 1. This would be the exact value. But here we're using differentials and approximations, so it's okay to use decimal values. However, when we use decimal values, I always tell my students 4 decimal places of accuracy, but when you're doing your math, keep everything as exact as possible, which means do all your math with this value, and then provide the decimals after you've done everything. Okay, so here I'll give you like a 5 or 6 decimal point approximation for this, but if I'm going to continue to do math using delta y, I am not going to use this decimal value. I'm going to use the exact value. That way my values stay as exact as possible and I don't have some compound error from rounding over and over and over and then using math with these rounded values, right? So my dy, we have a formula for this. So following that formula, remember delta x is 1/2. And then plugging in 1/2 to f prime will give me the following values, right? So e to the 1/2 times cosine 1/2 minus sine to the 1/2. Plug this value in. I'm going to give my decimal approximation. I get 0.328224977. Okay. So then this is the difference between delta y and the differential of y. Notice that they're fairly close in value. They're not super far off, but they're not the same value, right? So my error in my linearization at x equals 1/2 is going to be the difference between my value when I plug in my linearization, so plugging in 1/2 into here, and my function value. So me plugging in 1/2 to my actual function, so e to the 1/2 cosine to the 1/2 minus basically 3/2, right? Okay, so my error at 1/2 is my function value at 1/2 minus my linearization at 1/2. So here, if I plug this in, it's 1.446889037 minus 3/2 or 1.5, and that difference is a little bit less, which makes sense because as we saw from the graph on decimals, my function is under the tangent line, so it makes sense that the error is negative because my function is under the linearization. It's my linearization will give me an overestimate. It'll be larger than my function value, so the error is negative in this case. Okay, which is why we generally take the absolute value. So we just talk about how far away it is, and we don't really focus on whether or not it's over and under, which generally should just be apparent from looking at our functions, right? So here, LF has an overestimate, and again, we could tell even without this being negative, just because my linearization value is larger than my function value. That's really the easiest way to tell if it's overestimate or underestimate, which one is larger in value, right? So that's why we generally take absolute value for this. Okay, so my linearization is larger than my function at that point. Notice that if I take my error, not at 1/2, but my error function, and I look at the distance for my point of interest coming close, basically delta x coming to 0, it's going to go to 0, right? Because I'm not going to have any error, right? So basically what this is saying is if I'm a distance away, obviously there's a difference here, right? But as this point moves closer and closer and closer to being just p, well, the error gets smaller and smaller and smaller until there's no error. So the closer I am to my point of interest, right, to my tangent point, my point of similarity, the smaller the error is going to be. So that's really just what this limit is saying here, right? So as I move closer to my point, my error goes to 0.